Hello students, here's 65, and I'm just going to let you know up front, I did this problem just to make sure that everything went well, because there's quite a bit of plugging and chugging once you get the final expression, and then a surprise. And I'll let you know what the surprise is while I talk you through the problem. But here we have two masses sitting on inclined planes. One's pitched at 51 degrees, the other one's pitched at 21 degrees. So the two masses are connected by a cord, passes over a pulley, frictionless, and the system's going to accelerate. Now, it says initially that A moves up and B moves down. So there's an initial speed, okay, for these two masses. But that doesn't mean that the acceleration is going to be wholesale in that direction. And I did a little prefiguring in the beginning, and I determined that this mass of the acceleration of the system is actually decelerating. So m sub a is slowing down and going up the inclined plane attached to b, which is slowing down going down the inclined plane. So surprise, surprise, the acceleration of the system is negative, even though we're going to establish the direction of the initial velocity of m sub a and m sub b in the direction m sub a up the plane connected to b, m sub b going down the plane. And this will be clear once I get going with drawing all the vectors. So without further ado, let's go through a checkbox. The first checkbox is, what's the state of motion? Yeah, we're going to assume it's acceleration because it says determine acceleration. The next checkbox, sum of the forces equals 0, 0, or ma. Correct? Sum of the forces equals ma. And sum of the forces along the line of action, by the way. And the third checkbox is label the diagram. So labeling the diagram, we're going to label all the forces acting on those two masses along the line of action. I'm going to leave out the perpendicular forces and components because this diagram can get quite cluttered. But let's review some of our components though, especially for gravity. The component of gravity along the line of action, the parallel component, is mg sine theta in general. The component of gravity perpendicular to the inclined plane, okay, which we associate with the normal force, okay, which is equal to mg cosine theta. And the equation for the force of friction, we have mu times F sub n. Now, in this particular problem, we have coefficient of kinetic friction, so sliding friction times the normal force, okay, for which the normal force is mg cosine theta. So let's label this diagram. Okay, I'm going to use some red arrows, and here we go. So we have the tension of the cord, tension acting on m sub a, and the tension on the cord m sub b. We have the force of friction between m sub a and the inclined plane, and it's opposite the motion. So the initial motion is up the plane, so the force of friction is down the plane. Also true for m sub b. So it's opposite the motion. So there's your two forces of friction. Now here are the components of gravity. And they always act downhill. So we have component of gravity on m sub a pointing down the inclined plane, the component of gravity acting on m sub b down the inclined plane. Yeah, if you cut the cord, which way the mass is going to slide? Downhill. All right, so hence, force of component of gravity always acts downhill. All right. Again, I'm not going to list the perpendicular components or m sub b just because it gets cluttered. But let's label these vectors. So we have the tension in the cord attached to m sub a. Here's the tension in the cord attached to m sub b, Ta and Tb. Oh, and since the pulley is massless and frictionless, Ta is equal to Tb. Okay. Here we have the component of gravity on A, parallel. We have the force of friction, okay, between m sub a and the surface. So we'll call it F sub Fa. And over for mass m sub b, we have the force of friction between m sub b and the surface, and the component of gravity, F sub g parallel sub b. Notice a lot of subscripts there. All right, so let's add up all the forces along the line of action using Watt-Loa. Walk along the line of action. It's kind of a silly term, but it's helpful. I think it reduces the sort of the clutter that comes with applying the bubble technique. And if you find the solution online to this problem, you're just going to go, what? And that's just too much work. So we're going to simplify some things here. Yes, if you're asked for the tension in the cord, just bubble either m sub a or m sub b, and be done with it. But let's apply the Watt-Loa method. So imagine you're this mythical figure inspecting the line of action, and the line of action is up this side and down the other. Okay. And so the first two forces that you're inspecting that you come to are both pointing opposite the direction you're adding. So we're going to list those as negatives. So that's going to be minus f sub g parallel sub a minus f of f of fa. And then we have plus t sub a. Okay, we're going up the plane, over the pulley, down the other side. The next vector is minus tb, okay, pointing opposite direction which we're inspecting. We have another force of friction, okay, between mass of b and the surface. And then we have positive f sub g parallel sub b. And the sum of all those forces along the line of action are equal to the mass of the system because they're attached by a cord. So they pull on each other. They resist each other's change in state of motion. M sub a plus m sub b times the acceleration of the system. All right. Let's specify what each of these represent, each of these forces. So m sub g parallel. So I'm gonna start with what's positive and go left to right. So m sub g is m sub b g sine theta. Now the angle is theta b, which is the 21 degrees. The next force is the force of friction. So that's going to be minus mu sub k m sub b g cosine theta b. Remember, mg cosine theta b, that's the normal force equivalent, being the perpendicular component of mg. The next vector is the force of friction between m sub a and the surface. So that's going to be mu sub k once again. But instead of m sub b, it's m sub a g. Instead of cosine theta b, it's going to be cosine theta a. Okay, got to differentiate those two angles. And then last but not least is the component of gravity, which is acting downhill, opposite direction we're adding. That's going to be m sub a g sine theta a. That's 51 degrees. And all that's equal to the mass of the system, m sub a plus m sub b, times the acceleration of the system. Okay, now I'm going to leave it at that. The rest is algebra. Okay, so algebra, crush fingers. All right, when you plug and chug all that stuff in, 0.3 for the coefficient of kinetic friction. Mass of A is 2 kilograms. Mass of B is 5 kilograms. The angle of 51 degrees, 21 degrees. Keep it all straight. And you're going to get the following answer. You're going to get A is equal to, let's see, I'm going to look at my calculator because I did this before. You're going to get minus 2.156 meters per second squared. Yeah, you're going to get a negative acceleration. That's because the system is slowing down. It's decelerating. M sub A is slowing down, going uphill. M sub B is slowing down, it's going downhill. Uh, so expect that it happens, but that's all based on the fact that it's initially moving in the direction, so it allows to establish the direction of the friction force. Yeah, just think of the other questions that could happen. Okay, when's the system come to a stop? And if it does it start to accelerate in the other direction? I don't know, but let's just leave it at this. That's all this question asks for. What's the acceleration of the system in massive? So what do you think? All right. Have a good night, and the next video will be problem 67.